Okay, without further ado, Jules is going to be continuing talking about applied category theory.
Thanks. I'd like to thank the organisers for not giving me the 9 a.m. slot. I want to just quickly start by clarifying something that on Tuesday, I defined comonoids as satisfying an equation like this. So it's like if I have n branches here and m branches here, then I have n plus m minus 1 branches here, just by counting. And I just wrote an equation between string diagrams without clarifying what do I mean when I write an equation between string diagrams. And there are two different things this could mean. The minimal thing that this could mean is that I have a bunch of symbols in my generating data, and I kind of have a additional requirement that whenever I take evaluation of that generating data in some monoidal category, I require that the meanings of those symbols satisfy this extra equation, right? That's the minimal thing I could mean when I write an equation like that. But I like to actually think of this as an equality between diagrams. And if you like look at it, right, you can imagine like this is a topological move. So I usually think of this as I'm actually equating these diagrams by saying that there's some topological move I can do to push them together or pull them apart. And that's a very common theme in monoidal categories, is that not always, but very often, reasonable algebraic equations correspond to reasonable topological equations. So kind of not always, but often you can get away with saying that I actually equate these diagrams, and this is kind of reasonable. And by reasonable, I mean it preserves the intuition for diagrams that you already have. Okay, cool. So here's a important definition. A supply of comonoids in a monoidal category C, in a symmetric monoidal category C, is going to be a choice of comonoid structure on every object. So a comonoid commutative comonoid on every object compatibly. And what do I mean by compatibly? I mean that if I have an object that's a tensor product, x tensor y, and I copy it, so this is x tensor y, this had better be the same as individually copying the x and the y, and then swapping these over. So this is now x, y, x, y. Now, this is a having said often but not always, we get reasonable topological equations corresponding to reasonable algebraic equations. This is a non-reasonable topological equation because I failed to preserve the number of strings. So this is now an equation between the valuations of these things. So this just says that however I copy x tensor y must be compatible with the way that I copy x and the way I copy y. And really, you need to have a symmetric monoidal category to say this. You actually can't state this in a non-symmetric monoidal category. And the other thing is that there's some other equations. If I delete x tensor y, that'd better be the same as deleting x and deleting y. If I copy the monoidal unit, that should be the same as the diagram I've drawn here. So the monoidal unit is empty space in a string diagram. So if I have some empty space and I copy it, I still have some empty space. Empty space means the identity morphism on the monoidal unit. So this is really saying the identity on the monoidal unit. And similarly, deleting nothing is also nothing. Okay. So it's an additional structure on category? Yes. Okay, so yes, it's a. For every object Yes, there's a choice of comonoid structure on every object, which are compatible in this way. There is an additional way that they could be compatible, which we do not want to assume. So I could ask that this choice is natural, but I don't want to do that. This is like, this might be really shocking if you're used to category theory, because in category theory, you always ask that everything is natural. Supplies of comonoids are usually not natural. So I'm going to explain this carefully, because this actually motivates a lot of stuff. If this was natural, then this would say that, so basically that this choice would commute with arbitrary morphisms. So for example, if I have some morphism from x to y, and I copy the y, now I have two y's, this would be the same as first copying my input and then applying f to both of them. And similarly, having some f and deleting it would be the same as deleting the input. So if you think about what this means, this says that like running a function and copying the result is the same thing as running the function twice, and running a function and deleting the output is the same thing as deleting the input and not running the function. And like, so if your functions, if you think about programming languages, if your functions are pure, these equations are true, at least extensionally. But as soon as your functions do any kind of side effects or any interesting computation, these equations are just outright false, right? Running a function and deleting the output is not the same thing as not running the function at all in general. So we, as a rule, do not want to assume that this thing is natural. So, I mean, the reason in the end is that there's heaps and heaps of examples of these things that fail to be natural. So my favorite theorem says C has a natural supply of commutative comonoids if and only if the monoidal product of C is actually a Cartesian product. So this kind of says that, well, the reason I love this theorem is that this is a universal property, whereas this is something you can state with equations between diagrams. So this is a case where we can say something universal just by drawing a bunch of diagrams, which I really like. Like that's not always the case for sure. So the reason that we don't want to assume naturality of our supply of comonoids is that we really care about non-Cartesian monoidal categories. So here's an example of this thing failing in practice. So let's talk about. I'm going to randomly switch colors just for fun. Kleisli category. That's a delta. The Kleisli category of the probability monad, finite support probability monad. So this thing has a supply of comonoids. In fact, every Kleisli category on set has a supply of comonoids because you take the copy and delete maps from set and you can lift them into the Kleisli category. Right? Every morphism in set is still a morphism in the Kleisli category. But they fail to be natural. So here's an example. So we have a morphism, I'll call it C, going from 1 to heads tails. This is a morphism in the Kleisli category, so it's a Kleisli morphism of delta, and it's going to be flipping a coin. So it's going to go to, say, 1/2 heads plus 1/2 tails. So if our supply of comonoids was natural, that would mean that flipping a coin and copying the result would be equal to, remember that copying nothing is nothing, so I'm going to be implicitly copying nothing on the left-hand side of this diagram. Is flipping a coin and writing down the result twice the same thing as flipping two coins? No, it's not. And in fact, so these two things have the same type. They both go from 1 to heads, tails, tensor, heads, tails. So the underlying set of this is the Cartesian product. So this is a Kleisli morphism from 1 to heads, tails squared. And we can just we can calculate this. We can figure out what these comonoids actually are, and we can run the calculations, and we'll find that the left-hand thing takes star to a distribution which is with probability 1/2 the pair heads heads, and with probability 1/2 tails tails, and this one goes to 1/4. Okay, you know how this is going to go, right? We might get the same. We might get a different result from the two coin flips. So, like, this equation is false. Okay, it is true in this category. So, a neat thing about the probability monad is that it's affine. Affine means that delta of 1 is 1. There is only one probability distribution on a single point. Namely, you have to be that point with probability 1. There's nothing else you can be. That actually implies that the monoidal unit is terminal in the Kleisli category, which is kind of neat. So what that means is that the corresponding equation is actually true. It is true in this Kleisli category that running a function and deleting the output is the same as not running the function. So somehow the effect of probability is something that you can delete but not copy. So why is this true? These both denote, so x, y, x. So these both denote some Kleisli morphism from x to 1. The delta of 1 is 1. So, like, there is only one morphism from x to 1, no matter what x is. Okay, so this example is actually the prototypical example of what's called a Markov category. So a Markov category a Markov category is a symmetric monoidal category plus a supply of commutative comonoids, supply of commutative comonoids such that and it turns out that this is a really convenient foundation for doing probability theory. So there are examples of Markov categories that are not probabilistic. So, for example, the category of sets. Okay, if you squint really hard, you can view the category of sets as a theory of probability where the only probabilities are 0 and 1, and your probabilities have to sum to 1. So that implies that you can only output one thing. You have to be you can only be a Dirac delta distribution. But yeah, it turns out that this. Yes.
I was wondering that you showed that the monoidal unit being terminal implies that that equation that is the other direction true.
I believe I think Yeah, I think those were equivalent. Pretty sure. Yeah. Yeah. Yes. Yeah. Okay. So yeah, a bunch of people work on these things. You can add a bunch of extra axioms to narrow down what the models of these things are. So people add extra models so that these things admit things like conditionals or Bayesian inversion, and these extra conditions you add all turn out to be kind of graphically reasonable in some sense. So this is nice. You can develop quite a lot of probability theory in this way without ever having to deal with measure spaces. Of course, measure spaces gives you a model of this. There is a probability monad on measure spaces called the Jury monad, and it's very scary, and it gives an example of a Markov category. There are also one of the reasons we do this way rather than just talking about probability monads is that there are also very good examples of these things that don't arise as Kleisli categories of monads. So, for example, stochastic matrices fails to be a Kleisli category for mildly annoying reasons. It's actually like a relative Kleisli category. But a more important example is Euclidean spaces and Gaussian Markov kernels fails to be a Kleisli category for all kinds of reasons. But it is one of these. Okay, so that's the thing that's the category whose objects are Euclidean spaces, Rn, and whose morphisms are things of the form something goes to like fixed matrix plus plus a multivariate Gaussian. Okay. I'm heavily hand-waving this. Okay, cool. This almost takes me to where I wanted to end yesterday, but I wanted to just talk about Cartesian syntax a little bit. So, if you do have a Cartesian monoidal category, that means that you have a supply of comonoids that commutes with all of your morphisms. And in that case, you can, without loss of generality, kind of assume that all of your morphisms have exactly one output, because if you have a morphism with two outputs, this thing is equivalent to copying the input and then doing some left projection. You can kind of split f into its left part and its right part. Namely, I'm basically defining f1 and f2 to be f and then delete the second output and then f and then delete the first output. You can now prove that this is equal to this with the equations you have. So you pull f through this and then you apply the comonoid equations. So as long as you only have single output things, this thing behaves like a term, right? It can say f of and I can f g, and I can write like g of f of x1, x2, x3, like that. And also because I can copy, let's say I could do this. Now this is saying that, well, this is x2, x2. And I might also have some other input x4, which I never use. So because I can copy and delete, I can use my inputs any number of times, 0 or many. So what you get is that if you have a Cartesian monoidal category, then the things which you can draw with string diagrams basically correspond to the things which you can draw with kind of traditional term syntax. So what this tells us is that string diagrams are kind of interesting in non-Cartesian settings. Like if if we're in a Cartesian setting, okay, unless you're a management consultant, you want to give this to your client, and you can't give them algebra, but you can draw them pictures. Most of the time, if you're Cartesian, these things are just easier to work with because we're used to them. Okay, cool. Let's go on to the beginning of lecture 2. What time is it? 1/3 of the way through, that's fine. Any questions? Good. Okay, so I'm going to talk about traced monoidal categories. So so traced monoidal category, or traced symmetric monoidal category, is a symmetric monoidal category plus an operation So whenever I have a morphism like this, so I'm going to label this like x, y, z, z. So I have an input and an output type that match. I have an operation that says that I also have a morphism, which I'm going to draw x, y, like that. So this thing is a morphism from x to y. So I have some kind of operator that takes morphisms of type x tends to z to y tends to z to morphisms of type x to y. So I say I'm tracing out z. So this is a kind of feedback operation, and these need to satisfy a bunch of equations. And it turns out that the equations that these need to satisfy are exactly the obvious graphical ones. So it says the ones that say that I can kind of stretch and squash these things, I can swap them, I can swap them over with other things, and then we, in this case, we do have naturality. Naturality says that I can slide something around the circle. This is probably the most subtle of all of the equations that a trace needs to satisfy. I like to separate this one off because there is actually lots of interesting categories which are almost traced but fail this equation. So there's lots of different rival definitions of generalized trace monoidal categories that weaken this in various ways. So how I like to think of this is as a model of feedback or a model of non-well-founded recursion. And that's actually why this equation often fails in examples we care about, is that if you have something that only has a well-founded recursion, then you won't have this in general. But you might have some weaker forms of it. Okay, so this is the first structure that the category of sets doesn't satisfy. So I've given you two different monoidal structures on set, the Cartesian product and the co-Cartesian product. Neither of them admits a trace. This shouldn't be very surprising because set is not a model of non-well-founded recursion. Like, you cannot write a non-well-founded recursion in the category of sets and expect it to mean something. However, we do get lots of models of it. So, for example, rel with its tensor product. Remember, the tensor product comes from the underlying Cartesian product of sets. Yeah. Yes. Yeah, that's a yes. I'm coming to that later in this lecture, hopefully, if I go fast enough. But yeah, actually, that reminds me to say something important, which is that traces are uniquely weird because in basically every other case that we care about, string diagrams have this amazing property that you can cut them up arbitrarily, at least with horizontal and vertical lines, and the subdiagram contained in each bit will mean something. It will denote a morphism of your category. Traces uniquely break that because this, like, I can't decompose the trace. Like each individual bit of it does not denote a morphism in my category. If it does, then I have a compact closed category, and I'm going to come to those later. So there are examples where I can do that, but in general not.
So how do you like induction of something like diagram?
Very carefully. Yeah. Yeah, very carefully. So you can do induction on diagrams where you say that every diagram is formed by horizontal and vertical composition. Now you have to say that every diagram is formed by horizontal and vertical composition and trace. But yeah, that's a bit of a kind of minefield. Okay, rel tensor is going to be traced. So if I have a morphism x z y z, this denotes some, actually I'll call it R instead of F. So this is some subset of X times Z times Y times Z, right? And I want to figure out what should be the meaning of this thing. X, Y, Z. So this is going to be some. So the trace of R is going to be a subset of X times Y. Well, I probably want it to be a set of pairs X, Y such that there exists a Z such that R, X, Z, Y, Z. And if I make that definition, then this satisfies all of the axioms that a trace needs to satisfy. As soon as I have a trace and a bunch of comonoids, I can do the following. So a supply of comonoids. Rel has a supply of comonoids because it's a Kleisli. Rel tensor has a supply of comonoids because it's a Kleisli category on set. It's the Kleisli category of power set. The meaning of copy, it's namely it's x such that x is an x. So I can do this. I can now produce a value from nowhere. So this is like in Haskell writing let x equals x in x. I can produce a value from nowhere, and now I can calculate. So this is why I can't do this in the category of sets, because this is saying that I can like generically produce an element of any set, and there's no reasonable way to do that. But in rel, so this thing is a morphism from the monoidal unit to x. So it's a relation from 1 to x, and it's going to be the full relation. It's going to be the thing that relates star to x for every x. So this is why not everything is traced, because categories which are traced need to have some morphisms in them to denote kind of stupid things like this, like bad recursions. I can do something similar. Like, you know, when I do this, I've implicitly done a calculation in my head that I've actually like cut up this diagram. Yeah, like to actually calculate this, you have to do some work. I'm just giving you the answer. Here's a related thing. So I can lift functions from set into rel. So let's lift the not function from bool to bool. So this is going to lift to a relation which relates like false to true and true to false, and it doesn't relate to anything else apart from those two. And now I can draw not, I can copy it, There we go. So now I'm asking for basically a fixed point of the not function. And of course, in the category of sets, the not function doesn't have a fixed point, but in rel it does. And if you work out what this is, so it's a thing of the same type. It's a relation from 1 to 2, and we're actually going to get the empty set, the empty relation. So, like rel has two different tricks that you can do to make sense of bad recursions. One is to give the full relation, and the other is to give the empty relation. Okay. Cool. Rel with its other Cartesian, other monoidal product. So the thing that you get from lifting the coproduct of sets gives you a byproduct in rel. It's a thing that's both Cartesian and co-Cartesian, and it admits a trace. And that's another. It's very different, but very interesting. So in rel plus, so suppose I have a relation x, z, y, z. So I've changed the monoidal product. So now this thing means some subset of x plus z times y plus z. So can I produce some trace for it? X, y. So the trace of R needs to now be some relation between x and y. It turns out we do have one. I'm going to relate x and y if there exists some finite sequence of z's, z1, zn, where n is possibly 0, such that, so this is saying, like, if I stick in an x, it could immediately be related to some y, and then I'm done. Or it could not, and it could only be related to some z. But I could take that z and stick it back in and say, is that related to some y? Well, if it is, then I'm done. But it might be related to some other z, and I can do this. If I can do this some finite number of times and eventually get a y, so this is like x. I'm going to skip writing the coproduct injections so I don't lose my mind. So zn minus 1 is related to zn, and then zn is related to y. And just like that, I've invented operational semantics, right? This is basically operational semantics, but I didn't ask for this. It's just fallen out of the categorical structure. So this satisfies all of the axioms of a trace in this category, in this monoidal category. So this is kind of, I think of this like a token machine. Like I stick in a token here, and I shake it, and I keep shaking it, and the thing goes round, and then eventually it pops out here. Okay. And there's another kind of important example, which is basically the same as this, which is in the category of partial functions. So the category of partial functions is the same thing, up to isomorphism, as the Kleisli category of +1, the Kleisli category of maybe. And the coproduct of sets lifts to a coproduct on partial functions. I think it might be a byproduct, but I'm not 100% sure about that. It's definitely a coproduct. This is because this happens generically because the embedding of a category, a base category into a Kleisli category is a left adjoint functor, so it preserves colimits. So like occasionally abstract nonsense is useful for knowing things quickly. So we get a coproduct on the Kleisli category always. And for partial functions, this thing emits a trace, which is basically the same as this one. So this is saying that a partial function is the same thing as a relation that relates every input to at most one output. Okay, maybe I should say this again slowly because it's important. So a function is the same thing as an ordinary function is the same thing as a relation that relates every input to exactly one output. A partial function is a relation that relates every input to at most one output. So once I see it like that, I can just read off basically the same definition, and it gives me a trace on partial functions. And the nice thing about that is I can start drawing flowcharts. So back in the Stone Age, programmers drew flowcharts for algorithms, and by doing this kind of thing, we can view flowcharts as string diagrams. Like flowcharts are string diagrams for usually for co-Cartesian traced categories. So there was one other thing we need, which is that in a flowchart, I might have two different incoming edges to some node, and because I'm co-Cartesian, I can merge. So this is the dual of the fact that in a Cartesian category, I have a natural supply of comonoids. In a co-Cartesian category, I have a natural supply of monoids. And I'm just going to kind of do this without explaining it, but this is because we have a merge operator that says if I either have an x or an x, then I have an x, and then I have an absurd operator that says if I have nothing, then I have an x. This thing is a commutative monoid. So that is to say it's like a comonoid, but I flipped all my equations horizontally. So I have this and I have this, and they satisfy the equations I want. So whenever I have two different things coming in, I'm implicitly merging them before doing the thing. Okay. So dually to in a Cartesian monoidal category without loss of generality, I can say that all of my morphisms have exactly one output. In a co-Cartesian monoidal category without loss of generality, I can assume all my morphisms have exactly one input. So let's draw a string diagram for Euclid's algorithm, which is the one that I wrote in my notes. So we want to compute the lowest common denominator of A and B. So we ask, does A equal B already? In which case, yes, we stop. If it doesn't, we ask, is A greater than B? If it is, then we say that A becomes A minus B. And if it doesn't, we say that B becomes B minus A. And then I loop back around. I draw that bigger than I wanted. I want to take up exactly half the board so that the other half could be the corresponding string diagram. So I can translate this into a string diagram. I have some input. I'm going to ask, does A equal B? If it does, I'm done. If it doesn't, I'm going to ask, is A greater than B? And then in these two branches, I'm going to do A becomes A minus B, or B becomes B minus A. And I'm going to merge these together, and I'm going to trace this out. So I haven't said yet what my valuation is. So so this is I'm going to end up valuing this in the monoidal category of partial functions with coproduct. And I'm going to end up, so I have all of these strings are going to have the same object. I have a single generating object, and I'm going to take that to something like pairs of positive integers, and now, so my A equals B morphism must go from X to X plus X. I did an example just like this yesterday, but without the trace. So it says that AB is going to go to left AB if A equals B, and right AB if A is not equal to B. And similarly for this, and then my A becomes A minus B. This is just going to go from X to X, and you can imagine what it is. This is all of these things are lifted total functions. So total functions are still partial functions. So this is going to go to A minus B, B, and so on. And so in the end, if I calculate the total meaning of this diagram, I ended up with a morphism from X to X, which is going to compute. It's going to take some initial AB, and it's going to give you the pair of the lowest common denominator twice. So here's the catch. Euclid's algorithm actually terminates, right? We can write a termination proof for it. This way of looking at it doesn't see it as terminating. This views it as a partial function which magically just sort of happens to be total, but we can't read that off the diagram. So this is, but that's the same with flowcharts. You can't read a termination proof off a flowchart. This is a kind of translation. This is proving to you that flowcharts are string diagrams with only minor syntactic changes. Okay. But yeah, because flowcharts contain loops, and the syntax of flowcharts has no way to enforce termination of those loops, we basically have to take their valuation in something like partial functions where we have a trace. Cool. Okay. I think that's everything I wanted to say about traces. Good. Now I can talk about compact closed categories, and I think I'm getting back on time. So, questions? Great. Amazing. Okay. Okay, this is going to be a slightly gnarly definition. A compact closed category is a symmetric monoidal category plus, for every object X, we associate a dual. We have a dual object X star, and we're going to ask that this is involutive. So X star star is X, or probably isomorphic, but it's fine. And morphisms, I want to get this the right way around because I can get these backwards. So we have morphisms from the monoidal unit to X star tensor X, and from X tensor X star to the monoidal unit, satisfying okay, well, maybe I'll immediately switch notation. So I'm going to draw this one as, so I'm going to introduce the definition and the notation simultaneously. This is more confusing than necessary, but kind of explains why the definition is the way it is. So if my object looks like that, the dual object looks like that, and vice versa. So duality graphically is reversing an arrow. So up until now, my string diagrams haven't had arrows because I had this progressivity condition that they always go from left to right. except when I wrote a trace. In fact, you don't have to write an arrow on trace, and many people don't, but I find it helpful just so you can see that that part of the diagram locally is going backwards. But now I need to start labeling my strings with an orientation. And this thing I'm going to draw as a turnaround this way, so x, x. So this thing, x with a left arrow means x star. This thing, x with a right arrow means x. And then this one is going to be this way. And now I ask for the obvious equations, which is that need to be okay. In the end, it doesn't matter if I get it wrong because I'm a symmetric monoidal category and I can swap things around. But it should be this way. So these are called the snake equations for obvious reasons. Okay. Cool. Oh, and most but not all compact closed categories in practice have the property that x star is equal to x. Then we say it's a self-dual compact closed category. So most but not all examples that arise in practice are self-dual. And if you're self-dual, then you can not bother drawing orientations on your arrows. Orientations on your wires. So very commonly you see people working with these with no arrows in sight. Cool. So let's go back to my favorite example, rel tensor. Rel tensor is compact closed. If you write down its type, you immediately figure out what it has to be. It's going to be self-dual. So in rel, the dual of an object is itself, and so I need to come up with some meaning for this thing. And this is going to be, so this needs to be a relation between the one element set and x times x. So it's going to be star x, x, such that x is any element of x. And similarly for this one, so it's x, x star. Okay, so rel is compact closed. It turns out that compact closed categories can never, ever be Cartesian or co-Cartesian. These are incompatible structures. So whereas we do have Cartesian and co-Cartesian traced categories, we never have Cartesian, co-Cartesian compact closed categories. Yeah.
Maybe see the question, why do we need a star when we define the relations?
Sorry?
Why do we need a star? Like, why is it a set of triples?
Oh,
not set of,
because
doubles?
the monoidal unit of rel, the monoidal unit is a one element set. So this thing is a relation between the one element set and x times x.
I see. So it's kind of like nested actually, right? So
yeah.
Okay.
Right. I could also have. I should also have. The same level of pedantry demands brackets.
Okay. Cool.
Like when I'm working in practice, I don't bother writing down the star. I was trying to be clear.
Okay.
Yeah. Yeah. I was about to prove this. So, I'll prove it for Cartesian, and the proof dualizes. So, in a Cartesian monoidal category, every morphism from no things to two things necessarily, so f necessarily splits like this. This is a special case of what I did earlier, that every function has, without loss of generality, exactly one output. And so what happens is that this must, so if we assume that we have a Cartesian compact closed category, then this thing must factor in some way. And then then I take the snake equation. So this thing is that, and then I do some small amount of topology to say that. This basically says that that an identity has to factor through the monoidal unit, and from there I can think a bit and deduce that every object is isomorphic to the monoidal unit, and so there I discovered that there is exactly one category which is Cartesian uncompact closed. It's a category with one object. Okay. Cool. I haven't talked about spans and cospans yet, and spans and cospans are going to be very important in my next talk. Yes. Oh. Yeah. Other way around. No, that's right. Yeah? Was that just you could write it down? Or was there a question?
Yeah.
Yes. Okay. Did you have a question apart from can I write it down? Okay. Okay. I mean, I'm probably about to erase it again, but enjoy it while it's there. Okay. Okay. I haven't talked about spans and cospans yet, and they're going to be very important this afternoon. Okay. How about I erase everything apart from the green? So, did Chris talk about spans and cospans? I guess not. No. Okay.
Yeah. The red is the blue. The red is very hard to read.
Yeah. Yeah. Is the green also hard to read?
Well,
Yeah. Okay. That's why Vikram wrote everything in blue. Okay. So. So span set is a category that you might not have seen before. Is a category where objects are sets and morphisms x to y are diagrams x, y, a. This thing is a little bit like a relation. In fact, it's a lot like a relation, because you can think of A as like the set of pairs of what in X relates to what in Y, and it projects down to both X and Y individually. Yeah, A is any set. Yeah. So for each diagram of this shape, I get a morphism.
So A is like an index of the hexagon.
No. A is so the Hom set from X to Y. You could say it is a set A together with a diagram like this. And how do I compose? Okay, well, first of all, what's the identity? It's going to be this thing. The identity on X is this thing. And so composition is a bit tricky. So I have something like that, and then I have something like that. How in the world am I going to compose these? The answer is that I take a pullback. So I take A times Y B. Okay, now you can talk about span C, where C is any category that has pullbacks. Fortunately, pullbacks in set are easy. We know what they are. They're subsets of Cartesian products. So, oh, and to complete the definition, sorry, I need to get a span from X to Z, and I'm going to take this as the peak, and I'm going to take the composite morphisms down the legs. Cool. So as long as we're in set, it's pretty straightforward to like manually calculate what these are. If we're in a generic category with pullbacks, then we have to do like actual honest to God category theory, and it's a pain. Okay. There is some annoying stuff to do with coherence. So span set is not actually a category, it's a two category, because these things don't compose strictly associatively, because pullbacks are only defined up to natural isomorphism. There are three ways of dealing with this. My favorite way is to, so the worst but easiest way is to just ignore it and you get away with it. You just pretend it's a category and nothing goes wrong. The middle best way is to quotient out. So if I have two different spans from A to B, from X to Y, I can say that these are equivalent if there's an isomorphism here that makes this commute, and then I quotient out that isomorphism. And quotienting in category theory is usually a terrible idea, but I can do that and I get a category. The best way is to take it seriously that this is a higher dimensional structure. In fact, the third best way is to say it's a bicategory, and the fourth best way is to say that it's a double category. But I'm not going to talk about higher categories because we'll be here all day. TLDR, there's some like slightly gnarly coherence issues to do with defining categories for spans. Don't worry about it, it's fine. This category is compact closed. Oh, I forgot to mention that every compact closed category is traced. Every compact closed category is traced. How is every compact closed category traced? Well, if I want to define this, I define it to be this, right? Except here, this was my strange thing where the trace is like a slightly weird thing that's like individual bits of it's not well defined in their own right. Whereas this actually is like built of the pieces of a compact closed category. And if you have a compact closed category, then this construction always satisfies the axioms of the trace. The co-Cartesian examples I gave you, rel with its coproduct and partial functions with its coproduct cannot possibly arise in this way because co-Cartesian monoidal categories cannot be compact closed. But rel with its tensor product, which was the first example I gave you, does come this way. And the two definitions I gave you actually correspond to each other. So the trace you get from that compact closed structure gives you the same trace that I told you. That's probably not surprising, hopefully not surprising. So these are kind of the same structure in some sense. You're standing up, which is a bit scary.
Yes. We're
out of time. Okay. What was I about to say? Okay, I was about to prove, I was about to tell you that categories of spans are compact closed. And then I was going to tell you about cospans and that they're also compact closed. And that's going to be okay for this afternoon.
Okay. If there's any questions?
Yeah. Yeah.
You say they are compact closed when they are in set or in general?
In general.
Okay.
Yeah. Yeah. If C is so technically, if C has all finite limits, then span C is compact closed.
Okay.